Thanks everybody for attending today. I'm going to start out with a reasonably short PowerPoint presentation to kind of give you some background, describe some of the problems that we're trying to attack. And from there, we'll actually take a look at the product and we'll give some demonstrations with some actual real data to show you some of the unique and novel features of the software. As you probably know, this software is targeted for qualitative unknown analysis. Although in the latest version 3, we've added a capability to do semi-quantitative analysis. I probably won't have time to go into that in much detail today, but I'll talk about it a little bit. This is our version 3 software. We're pretty excited. It's got some pretty revolutionary features in the software that really make it unique. We've listened to our customers and we've tried to implement and address a lot of their needs and issues with this version of the software. So with that being said, let me just start out and talk a little bit about Gcms Search in general, and just go over some of the issues of today's GCMS library search, qualitative analysis, unknown ID. First of all, GCMS Search has been around for a really long time, and it's a very, very powerful tool. The libraries have grown significantly over the past 30 years, and they're very good libraries, high quality, with a really broad coverage. Unfortunately, not much has really changed. Certainly, the instrumentation has gotten better. The instruments have become more sensitive and more reliable, but the basic process of unknown ID using library search hasn't changed. So let's look at some of the limitations of the current library search for qualitative analysis. First of all, library search, when you do a library search, you search an unknown against a commercial library or a user library, and it returns a hit list, which is a sorted list based upon an algorithm which compares the unknown with the library matches. And the list is in order of the best to the worst, and usually you return maybe 20, 30, 40 matches. The problem is that the search hit lists, they're not definitive. What that means is that the best match in the hit list doesn't necessarily mean that's the correct match. There's significant variability in GCMS measurements from instrument to instrument and from vendor to vendor. And that variability contributes to this problem. So the top hit isn't always the best match. In fact, a lot of times it is not. The other really big problem is co-eluding chromatographic peaks. If you recognize them, you have to figure out a way to try to get around the mixture and search the pure components. And if you don't recognize that the peak is a mixture peak and has co-eluding compounds in it, you can return very misleading search results. They can be wrong, they can be very poor, and you don't necessarily understand why. You don't understand whether it's a mixture peak or maybe the compound isn't in the library. It's a big problem. And then finally, since these search hit lists are not definitive, you really would like to have additional information to help validate the search hit list. And as we all know, good analytical practice, really requires that some additional metrics, not just one metric, which would be the search match, should be used to confirm the matches to get a better level of confidence in your match. This is what a typical hit list looks like for a compound using library search. In our product, the actual library search engine we use is the Nist search engine. They actually provide an API and to their software, which enables us to use their algorithms to do the search part of Gcid. And this is what might be returned. This is actually a real search. This is probably a worst case scenario, but if you look at the hit list here, you have the hits listed in order of best to the worst. Now in the Nist search, I look at the similarity search, and the similarity, if the compounds in the library of the unknown in the library match exactly, you get 1,000 return. Now, very rarely does that happen, but usually if you get up into the 900s, that's an excellent match. And then you get below that into the high 800s, it's usually considered a good match. And then below that, things get a little dicey and you have to be very careful. So in this list, what you see is that the Nist similarity match that's returned for the first 18 compounds is all above 900. So they're all really excellent matches. So which is the correct match? So a lot of people say, well, it's got to be, the computer says it's the top match, it's got to be the best. That's not necessarily the case. And in fact, many times it's not the case. And in fact, in this example, the third match is actually the correct match. So, how do we get better confidence, get better answers? We have to add some additional capability in order to confirm these search list metrics. And as I talked about the coelution problem, for example, this peak here at about 3.13 or thereabouts, if you look at it, you say, well, it could be a pure peak. You do see a little bump on the side. Maybe it's a mixture peak. And if you just perform a search on it, what you'll find is you'll get a hit list return, which has very low search values returned, which indicates a poor match. And the problem is, of course, this particular peak is indeed a mixture peak. So the next thing we can do is we can use some form of deconvolution. And when you do that, in a deconvolution, what you can do is mathematically, you try to identify the underlying spectral components of the peak. And there's a lot of different ways to do this. And what happens is if you get it right, and you don't always get it right because it's a difficult mathematical thing to do, you'll get two pure component spectra. And then you can search them independently. And now you get good search values and you get correct matches. So here you can see a nice 906 is methyl isobutyl ketone is the first match, and then it starts to fall off. So you have a good confidence that's the right match. But if you look on the second compound that's coeluting, you'll notice that the top three matches here all have very good scores. And that's because, of course, these are these compounds are isomers, and they have very similar spectra. So how do we differentiate which is the correct match? So those are the challenges that we have. So how do we improve this search confidence? Well, we already talked about the identification of mixture peaks. And one solution is, of course, is to go to try to do this deconvolution. We take a slightly different approach from the way most people do deconvolution. Our approach is actually a two-step approach. What we do is we first use a statistical method to look at all the spectra across the peak called principal components analysis, which you may have heard about. And it's a very powerful statistical tool. And what it tells you how many independent variables are across or within that particular peak. It doesn't tell you what the pure spectra look like, but it's very good at telling you how many independent components are in there. Once we know how many independent components are in there, Then we can try to use more conventional techniques to deconvolve the mixture peak into its pure component spectra. This approach, and also it also will address column bleed. And the nice thing is it's very automated. There's no parameters that you tweak. It just goes and it can work. Some of the advantages of this approach is that it doesn't overfit. A lot of the conventional algorithms, they'll tend to return a large number of underlying compounds, and it's not real. And so it's kind of fraught with error if you're not careful in setting up the parameters. So this approach tends to be pretty robust. The other issues, of course, is how do we provide some kind of complementary or hopefully orthogonal other metrics that we can use to confirm the identity from the hit list. Well, one thing we can do is, if we have an accurate mass instrument, is we can do accurate mass formula ID. And the idea is, if there's a molecular ion, not all compounds in EI have molecular ions, we can determine the formula and see if it corresponds to that particular compound. That's one nice thing. We can also look at the fragments, and we can actually do formula identification of the fragments. This is also useful. It's particularly useful if we have a search a compound and it's not in the library. Looking at the fragmentation can give us some ideas to what the actual underlying compound is, even if it's not in the library. And then the other one, which is a really powerful and truly orthogonal metric, is retention time index. And again, we want to implement this in a system that's highly automated so that it just processes an entire run and returns you the right answers, hopefully. Retention index is really interesting. The neat thing is today, they're readily available retention index databases. The new Nist 20 database has pretty much 100% of the compounds have assigned retention index values. So it makes a really comprehensive, powerful metric that we can use to help us make better decisions and improve the confidence of our reports and our matching. So I said it's an excellent orthogonal metric. It's really good for distinguishing between isomers. This is something that mass spectrometry isn't particularly good at. And the other thing is that your GC can be pretty readily calibrated for retention index in an automated fashion with commercially available standards, such as a series of N-alkanes, which is a common calibration standard. You don't have to use N-alkanes, and we'll talk about that a little bit. You can actually use other compounds as long as they're spread across the chromatogram at a reasonable density. You typically do have to use an additional run to run this calibration for retention index. That's, sometimes it's not convenient. Sometimes people find it a little difficult. And this is some of the feedback that we've gotten from our users. And we thought about this, and we've actually come up with a very unique new algorithm, which we call Auto-RI. And it's a way to get retention index from the sample data itself. So it doesn't require standards, and it allows you to get the retention index information on any data, even if you've never run a standard. It can be an old run that you did 10 years ago, or it can be a run that you run in the lab yesterday. So it's pretty exciting, and we're going to talk about how that works as we move along. Formula ID. Now, obviously, if you have an accurate mass instrument, you can get formula identification to help you confirm the Nist matches. And again, as I said, you can do the formula ID for the molecular ion, for fragment ions, and it's helpful to get information for compounds that are not in the Nist, not in a library. But of course, most people don't have high resolution GC instruments. So what we'd really like to do is get that information from our workhorse single quad GCMS instruments. So how do we do that? It actually turns out it's pretty readily done. This is where Cerno got its start about 15 years ago, is introducing this technology. And the basic premise of it is that we first acquire the mass spec data in profile mode, and then we perform what we call a peak shape calibration. And we'll talk about this as I move along. And what this allows us to do is it allows us to significantly improve the mass accuracy from your quadrupole. And maybe more importantly, it allows us to improve what we call the spectral accuracy. And with these two different metrics together, we can achieve very reliable formula identification. So let's see how that works. Normally, when this is an actual spectrum from a quadrupole, and at resolving power 800. And this is what you'll typically see on your computer screen. And this is just a single ion at around 400 m/z. And what the computer shows you is it typically shows you the data in centroid mode. So basically, they're sticks, okay? And what they really are, they're sticks of where the mass spectrometer has peaks, because what the mass spectrometer is really measuring underneath is what we call profile mode data. Sometimes vendors call this raw mode, and sometimes it's also might be called continuum mode. And so as the quadrupole scans, the detector sees the ion current in a continuous fashion, and you actually get a continuous series of peaks where this is A plus 1, A plus 2, A plus 3, so on and so forth. And then normally what happens in the instrument software or firmware is it does the centroiding operation. But when you do that, there's a lot of information here that you're going to throw away. So when we actually work with data to get accurate mass, we require that you acquire the data in this profile mode. And pretty much all modern instruments can do this. Even older instruments can do this kind of data acquisition. Why is it important? Well, for example, this is a series of compounds. It happens to be LCMS, but it's the same problem, that are actually within probably 1 ppm in terms of mass position. So even with a very high resolution, accurate mass instruments, it would be very difficult to determine which of these formulas is the correct one. Because if your instrument specification is 5 ppm and these are within 1 ppm, you're not going to be able to distinguish them by mass alone. However, you think about mass spectrometry, and these are synthetic spectra, so we can generate these using a computer. That's the beauty of mass spectrometry. We can do that. And if we look at the different spectra, you see that there's very different isotope profiles dependent upon the formula, which of course, has to do with the isotope distribution of these different formulas. So it's another very powerful tool, if we can match it accurately, to help us identify formula in addition to mass accuracy. So it can further improve the mass accuracy by giving us another metric and to get even higher reliability in our formula determination. So how do we achieve this? Well, as I mentioned, we acquire the data in profile mode. And at the end of the run, you set up in your method, in your GC, to turn on the internal calibration gas that's built into the instrument, the PFTBA gas. And what we do is we use this as our calibrant. And the nice thing about the gas is it has a number of known ions across the whole spectral range. And we can use this to calibrate these calibration ions to correct for the mass error as well as for the peak shape error. And we can calibrate the peak shape to a known mathematical function. So what does that mean? Well, if you look at this plot here, there's 3 overlays. There's the blue overlay here. That's the uncalibrated data. That's real data. That's actually a real plot. And that's what the mass spectrum in profile mode looks like. And what you'll see is you'll notice that the peak here is it's not a pure Gaussian. It's not a mathematical function. It's a somewhat arbitrary function, which is dependent upon the tune of the instrument. And it's typically asymmetric. It's not it's consistent from run to run, but it's not directly model. You're not able to model it directly, because what we would like to do is we'd like to calculate the compound, that spectrum that we think it is, and we'd like to match it. So if you look at the red line here, that's actually the calculated spectrum for this compound here. This is the uncalibrated spectrum, which is very difficult to match because we don't know what that peak shape function is. But what our calibration does is it calibrates the spectrometer peak shapes to a known mathematical function. We can actually write the equation down. That allows us to compare the calibrated data, since it's calibrated to a known line shape or peak shape, to the calculated data. And with that is called spectral accuracy. If we can match that isotope pattern very accurately, gives us another metric for formula ID. So in this example, that's the formula. The exact mass is at 210.088, and the measured mass after our calibration is about 210.0931. So that's about 4.5 millidalton mass error. That's excellent for a quadrupole. In real life, this is an example of a really good measurement. In real life, you typically will tend to get between 20 and 30 millidalton mass accuracy on a quadrupole for real samples. But in addition to that, since we can now match the isotope pattern, we can use that additional information to pin down the correct ion. And in this case, we have a spectral accuracy of 99.5%. So that means that the calibrated ion explains 99.5% of the calculated. So that's our magic. That's our trick. But how does it also improve the mass accuracy? Well, if you look at it, yes, a quadrupole has, has fairly broad lines or fairly broad peaks here. So if you don't calibrate the peak shape here, how do you find the centroid data or the accurate mass position? Well, you have to look at maybe the single point that's the maximum. Maybe you can use a few points over the top. And, with instrument noise and such, that's not that great a way to do it. It's not super accurate. And in fact, most vendors will give you a specification of about 0.1 Dalton for mass accuracy. But once you do the calibration, instead of just fitting the peak, since we know what the line shape is, we can actually fit that mathematical equation, that function, over all the points across the peak. That's a much more accurate way to find the centroid or the central location of that peak. So with that, we can now determine our mass accuracy down to about the third decimal place. So it's about 100 times better than what you would normally get. And then finally, we can use this spectral accuracy to help us do the identification as well. If we don't calibrate the peak shape, we're trying to compare calculated spectra using some line shape function that is not going to be the same as the instrument. So you're not going to get a good match, as you can see. But once we calibrate it, we can get really good matches. And these matches are very sensitive to the formula. And that helps us get an effective mass accuracy that's really, really good. Now, obviously, you're always going to do better with a higher resolution instrument. You have more sensitivity, you have better resolving power. But on our workhorse quadrupoles, we can now do very, very confident formula identification. So that's the other metric that we can use. So this is proven technology. Like I said, this is where we got our start in the business, and it's been published in hundreds of publications. If you're interested, at the end, we'll point you to a journal publication that describes the details of actually how the mathematic works. But it's even used by organic chemists to verify their the formula of their newly synthesized compounds, and is accepted by journal publications like ACS, for example. So let's put it all together now. This is now a new hit list which I've added some additional information to help us identify the correct match. So as you can see, the top 3 compounds all have excellent matches in terms of the Nist search and also the reverse search. And we're going to talk about that a little bit and why that's really important. So how do we decide which is the right match here? Clearly it looks like the top 3 candidates there are probably one of them is correct, but which one is it? So the first thing we can do is remember our spectral accuracy. That gives us that basically combined with mass accuracy can confirm the formula of this particular hit from the Nist search. So what that says is that if 100 would be a perfect match, is that we have a spectral accuracy of 99.28%. That's a very highly confident formula valid verification. So that says, okay, that formula is correct. So we have another thing that validates that particular compound. We can also look at the fragments. They're not so important at this level, but if you start to look at compounds that aren't in the library, it becomes a more important kind of metric that you want to dig into and look in a little deeper. The other one is the retention index, which we talked about. And what we have here is this RI lid value. That's the value that's read out of the library. So I read out of the library that this compound, 1,2-dichloroethylene, has a retention index of 609. We've calibrated the instrument, or the GC, and we've determined that the retention index of that peak is 563. Now, if you look at that, that's about 55 or 54 IU units away. That's a pretty big shift. So that's likely not to be the right compound. To make it a little easier for you to read, we actually come up with a metric called RI fit. And what it is, it's just the difference between the library and the calculated retention index minus 100. So 100 is a perfect RI fit match. And 54 would be about 40, about 45 or 46 units off. If you look at the next compound, again, the matches are all good. The formula is confirmed. But the retention index fit is not that great. If you look at the third compound, you'll notice that indeed it has a very good retention index fit. So in all likelihood, I have a high degree of confidence of saying that's the right match. And you'll notice how this is color coded. And this is actually what we do in the product. It makes it visually easy for, normally you'd have to go through and look at all these numbers and, try to, in your head, try to figure out, which is the best match. But we can let the computer do most of that work. And what the computer does is it looks at all these metrics, and it basically, in this case, it said the retention index is way too far away. There's no way that's the right compound. Even if it's got the best Nist search, it can't be the right compound. And likewise, here, it's not the right compound either. But here, now it's got a good retention index match, and it's got a good Nist match, and it's got the right formula. That's the right match. So that's the value. So now that I've determined, and notice these are all isomers. So that's the value of using these additional metrics. I can determine correctly the compound that otherwise I'd have a very difficult time doing. So what would you rather look at? Would you rather just look at the Nist search values or any search, whatever search product you're using, and use that to make your judgment call? Or would you rather have all that additional information? I know what I would want. I would want that. Now, very quickly, I just want to talk a little bit. Not everybody may be familiar with forward and reverse search. With forward search, what the algorithms do is it matches each peak in the unknown to each peak in the library. But if there's extra peaks in the unknown that don't match up, then the score gets penalized, and so it gets reduced because there's additional peaks in the sample that are not present in the library. When we do a reverse search, what we do is we compare the peaks from the library spectrum to that of the unknown, and we look at the ones that match up and we calculate a score, but we ignore the peaks that don't match up. In other words, if there's extra peaks in the sample, we don't penalize it. So what that allows you to do is, if this is a mixture peak, what you'll see is that or if it's a pure peak, what you'll see is the forward and reverse scores will be very close to one another. If it's a mixture, what you'll see is the reverse search will be pretty good, but the forward search will be bad. So it's another way to utilize the search data to gain additional insight. Okay, so with that, we'll go to this slide at the end. I'm just going to start up the product right now, and I'll show you a few things and how it works and what you can expect. So the product is actually very simple. It's kind of like a list processor. And what you'll see is it's just a list of all the runs that I've processed. So I go, and again, it works with any vendor's instrument. It worked with Agilent, it worked with Shimadzu, it will work with Thermo, it will work with PerkinElmer. It's vendor agnostic. And you basically just point to the data run. The software reads it in and does all the peak picking and searching and calculations for you. It's a very automated process. So let's start out. What first thing I would do if I'm going to do a retention index, if I need this retention index data and this accurate mass data, is I got to run a calibration. So what you typically do is, if you look how I set up the run, you basically make a note. You say that this is a simple run of VOCs, or organic volatile organic compounds. And I just point the program to say, well, where is the retention index information? Where is it at? And it's just in the data file called VOC calibration. And likewise, where is the PFTBA gas for the spectral accurate mass calibration? It actually happens to be turned on at the end of the run. So it's in the same data file. And since this is the actual retention index calibration, just for sanity check, I would like to also analyze the data so that I can make sure that all the alkanes were properly selected, or my standards were properly selected. And this other field here, parameter settings, that just controls how the processing is done. So for example, actually most of these settings you'll never touch. The things that are probably most commonly adjusted are the peak picking parameters, what we call the instrument identifier. So what that does is when I build a calibration, the calibration is remembered under that name. So any other parameter file that I use has that has that name, it will use those calibrations that I generated. And then finally, I can choose which libraries to use to search. Here I've chosen the Nist libraries, the main and the replica library. And there's also Wiley libraries are supported. So here's all the Wiley libraries. If you can also use your user-generated libraries that are exported from your instrument, or that are built directly from our product, as a matter of fact. Then what you would do is you choose your column type. This corresponds to DB1, DB5, and wax columns. Those are the three column types that have retention index data for them in the databases. And then, of course, you need to tell it what alkanes I'm using. Again, I don't have to use them, but it's pretty common. A lot of people do it that way. And then the rest of this is just report customization. So for example, I can tell it to report the CAS number, I can get the hit number, I can get library types, I can get the forward and search. It's totally customizable. You just check off what you want to see. So once I run it, I can reprocess it. I've already run it once. I'll reprocess it just to show you how it goes. So it's going to recalculate the calibrations for the retention index, spectral accuracy, and then it's going to go and analyze the unknown, which is actually the alkanes in this case. So if you see this little window over here, what it's done, it's finished. And what all it's doing here is it's recording what processing has happened. And this log file is associated with the run. You can go back and look at it. And it said that it made a calibration. That's the name of the calibration, which is our instrument identifier. It went through and found these peaks at this location and assigned them to C5, C6, C7 in the alkane and alkane series. You need to check that to make sure that's okay. And then it went and reanalyzed the alkane themselves. And this is what the run looks like when I analyze it. So there's your alkanes. And as you can see, the retention index library, that's the value right out of the library. By definition, pentane is 500. And the retention index, of course, since I calibrated with the same file, it's going to be the same. But it's a sanity check to make sure everything's working okay. Okay, so now, once I've built those calibrations, and that's a one-time thing, you would typically, you'll need to probably redo the spectral calibration every maybe couple of days. And as long as nothing changes in your GC, that would be likewise. Some people like to do it every day. Now let's go and do the analysis. So what does the analysis setup look like? It's pretty simple. Oops, that's not what I wanted to look at. I wanted to look at, yeah, that's right. Okay. All I do is I tell it to analyze the unknown. That's the unknown, the source data file. And I just point it and I just use that parameter file, which tells it where to get the calibrations that I made. It's that simple. And I've already processed this run. So let's just dive in and take a look at it. So there's the run. It's a run of VOCs. I can zoom in on the chromatogram here. And what you'll see is there's a couple additional fields that I haven't talked about yet. One is that there's this quant field. The software can do semi-quant. You can designate target and reference peaks to be used based upon retention index or retention time. Retention index obviously is nice because it's pretty much method independent. And you can even tell it to use a standard that's found by the identification of the compound. So that's kind of unique. So it's quite powerful, but it's quite simple. The mix field, and if I don't set that up, it just reports the area. The mix field, it tells me which peaks are mixtures, and it tells me how many components are in each peak. So for example, here we have at 136, you'll notice there's 2 entries. So at that peak at 1.36, that little guy right there, you'll see that it determined that there's 2 compounds in there. So that's the first out of 2, and that's the second out of the 2. And likewise, for here at 1.5, it's the first out of 3, second out of 3, and 3 out of 3 that were deconvolved. And then it goes and searches the compounds that it deconvolved. Okay, so let's look at some interesting data here. I'll zoom in here at about like that. I'm going to scale it back a little bit. So what you'll see here is that we'll look at this peak at 235. So that's a mixture peak. It does look a little broad. Okay, so it's not surprising that it's a mixture. So let's click on it and look at the hit list, because what we're looking at, what we're looking at here is just for each peak, it gives the best Nist match, which of course isn't always the right match. And that's why we have the color coding here. And we'll take a look at that in a little bit, but let's look at the hit list. So we're going to dive down into that peak, and that's the first peak out of the 2 component mixture, 1 out of 2. And you get a nice search result here. And actually the top 13 compounds have excellent matches. So if you didn't have additional metrics, how would you know which is the right match? The spectral accuracy now in this case, the formulas are all the same. That's not unusual. In a lot of cases it isn't, but the spectral accuracy confirms the formula is correct. Okay, so you may not get a right match, but a lot of times you can get the right formula. But the important thing here, especially because these are isomers, is the RI fit values. So if you look at the RI fit values, you see that the Z form of the isomer has a retention index fit of 90, and the E form has a retention index of 77. Now it's not colored down because it's still a decent retention index match, but in general, that's going to be the right match. And then of course you can throw away a lot of these other matches. Okay, even though that has a good Nist search match, retention index is too far off. That's no way that's the right compound. You can throw all that out. So it makes your review process much more confident and much faster. So let's go look at another peak here. We'll go look at the peak at, I think it's at about 3.7 here. Okay, this is another mixture peak. Again, you can see the coloring. It highlights that this is a good match because it has, again, good forward and good reverse search. If they were really different, it would be suspicious that it was a mixture and it would flag it. Has a really good spectral accuracy that confirms the formula, and the retention index fit is excellent. So there's high confidence that's the right match. The next match, it's still got a good Nist match, and it's still got the right formula, but of course the retention index is not right. So right off the bat, you're able to confidently identify the correct match, and you would not be able to do that with just the Nist values, with just the search metrics. And I searched the replica libraries as well, so you'll see styrene pop up in the replica libraries. This says this lib field tells us that particular compound came from the Nist main library, and this compound came from this styrene came from the replica library. It's nice to look at the replicas because they kind of take into account the variability that we get from instrument to instrument. So it's worthwhile utilizing that kind of feature when you do searching. Okay, so we basically built a calibration, and then we went and analyzed the data. We got all these nice new metrics. We can do all kinds of neat things now. There was one other peak I wanted to look at in here. Sorry, I wanted to go look at the peak at 1.8 here, which is a very interesting peak. Why it's interesting? It's weak, okay? It's not that weak. That's the peak. And what you'll see on the match, on the hit list here, the Nist search, you'll see there's no blue. It's all yellow and red. So there's low confidence in everything. And if you look at the Nist search value, you'll see the forward search is poor. Not very good. But the reverse search is actually pretty good. So as we talked about, that's an indication that perhaps it's a mixture peak. Well, how come the deconvolution didn't find it? Well, if the peaks coalute too close in time together, you can't, no matter what kind of math we use, you cannot deconvolve the peaks if the retention times are right on top of one another. It's just mathematically not possible. But we can look at this Nist value and we can look at the reverse search and we can say, oh, well, it's probably a mixture, okay? And if we look at the spectral accuracy, we know that's the right formula, C6H6. It's got an excellent spectral accuracy, and the retention index is actually pretty good. So what's going on here? Well, if there's another compound in the mixture, that's going to throw off the search. So what we can do here is I can click on this, and now what I do is I just overlay the Nist library match with the unknown, and you can actually zoom in here and look at that. This is the molecular ion for benzene at around 78, and you can see that this is the overlay of the spectral accuracy, which gives us the formula identification at 99.39% spectral accuracy, and it's within 30 millidaltons. So we know that's correct. But if we look at the whole spectrum, what you'll see is that these peaks here are not explained by the match. These peaks aren't explained by the match, and they're really significant. And this little peak over here is not. So it's likely a mixture. So can we figure out what the other compound is? Well, if you go down our hit list, we know that if the compounds are coeluting, the retention indexes must be pretty close. So we look down the retention index till we find, or the RI fit value, till we find a retention index, which is very close to that. And that's a likely candidate. And you'll notice here that the RI fit value is almost pretty much right on top. The retention index is 654 and 663, pretty darn close. And that's why they're coeluting. The other thing to notice here is that for that compound, carbon tet, the reverse search is also really good. Again, that indicates that it's a mixture. And of course, what it might be mixed with is the benzene. So keep in mind here, the peaks that aren't explained by benzene here, these peaks, that peak, and that little peak over there. If I click on this guy and do the overlay, it's like, guess what? It explains exactly the other component. So even though I couldn't do deconvolution because the peaks co-alluded too close together, I can still use the information to tease out the pure component spectra and the identification of peaks that are co-alluding almost right on top of one another. So that's very powerful. Okay, let's move along here. I want to show you more. I want to show you one other example. Now what I've done is I run the same sample, but I didn't do a retention index calibration using a separate run. But I am going to do an accurate mass calibration. So you can see here what I've set up in the calibration is I've said this is the sample to analyze. This is where you get the PFTBA gas. It's actually from the same. It was turned on at the end of the sample run, but I'm not gonna give it a retention index calculation. But what we can do is we can actually calculate a retention index curve from this data. And if I go back here and I right click on this guy and I can say show auto RI curve, and what you'll see is a retention index curve. Now, what the software does is it goes through and it does the search and it does the best job it can, just like we discussed. Of course, it doesn't have retention index data, but it has the search, has the forward reverse search, it has the spectral accuracy. And what it can do is it can plot out only the highly confident matches. Okay, so it doesn't choose anything that has a poor match in terms of the spectral search. And if you plot them, you would expect, of course, retention index to have an ascending order. And we can fit that to a curve quite nicely. You can see how nicely these points lay on the curve because I've only cherry picked the high confident matches. But as we saw, you still can get confused because, and the only way you can discriminate a bad match is by retention index. So what we can do is we can fit this curve and then we can look for retention index outliers. So those are outliers that maybe are 2 standard deviations from the curve. And we know those are incorrect IDs. So we can throw them out and we don't use them in our retention index fit. Now you look at this curve and you see this initial shoulder and you say, is that real? Does retention index really do that? And the answer is yes, because a lot of times what you do and when you do temperature programming is you start out with an isocratic constant temperature. In this case, it was a few minutes, and then we turn on the temperature ramp. And if you remember anything about Kovat's retention index, for isothermal runs, it's a log relationship with retention index. But for temperature program, it's more of a linear. So that's pretty much what we're seeing here. But we can take that into account in the fit. So in this case, we haven't even had to measure an external retention index standard. So it can be used on any data whenever you've collected it today, yesterday, or tomorrow. So that's very powerful. And if you go look at the data, again, it's the same data set. You can see actually for the early runs, there's not as much red labeled here. So that means that actually the retention index is better for the early runs because it takes into account that dip in the isothermal. If I go here at the end, I look at this compound at 618. And what you'll see is, again, it's the top match is marked in red because it's not the right match, even though it has the best Nist search, because the retention index value is off. It's too far off. It can't be the right hit. Here, now that's a much more reasonable retention index. In fact, it's one of the best with a high search value. So that's the correct, I can say confidently, that's the correct match. So that's the power of this, is with using retention index and accurate mass to validate and easily identify with high confidence what the matches are. And now you don't even need to run, for most cases, not all, but in most cases, you don't need to run that additional standard, which is very attractive to a lot of people. Let's look at it something a little more complicated. This is an Alkane calibration for these are actually a plant product that's used to make fake meat. You probably know about these products that are coming to the market. And it has a lot of terpenes in it. The thing about terpenes is they all have the same formula or sequences of formula, and there can be tons of isomers. So here we ran the external calibration, and we can use that to do the analysis, but we can do the same thing without running it for this particular sample using this auto RI I just talked about. And so, for example, if I want, this is run without an external standard, and you can see again the auto RI curve, and you can see it looks really good. Okay, and the shape of this curve is usually dependent upon how the temperature programming is set up. It's very interesting, and these are the outliers that don't follow a trend in retention index, because we know the retention index has to constantly go up, and if they're out of line, then they're not highly confidently identified samples. So that's how we can do it without an external standard. And if we go and look at the data, we can take a look at it. It's pretty interesting. Let's go and look at this peak here at like about, I think there's some interesting stuff here on 10.1. So let's click on that guy. So we're looking at this peak here. This is the hit list. And what you'll see is, you'll see the RI, you'll see, oh, they're all the same formula. So yeah, okay, it helps that you have the formula in this case, but because there's so many isomers in these terpenes, it's of limited use in this particular case. So the only thing, and if you look at the search values, they're all really good, all the way down to like the top 12 or 13. So which is the right match? The only thing you have to go by is retention index. And fortunately, it's very good at discriminating isomers in this case. So what you'll see is the top match. It's a pretty decent retention index fit. So it's colored blue. This one here, 0 means that it's more than 100 IU units away. So we don't even bother reporting it. If it's that far away, there's no way it's the right match. So we color it red. So you can visually look at it. Now this match here, which is this particular isomer, has a very good retention index fit. And you can see that there's also a replica of it in the library. That's the replica. That's in the main. That's the same compound. Of course, they both have the same retention index, excellent fit value, and same formula. The search results are a little bit lower, but they're still really excellent. So with a high degree of confidence, I can identify the compound that previously, without this information, you would have very little hope to identify properly. Okay, with that, I'm going to open up for questions. I'm going to close the app here, and I'm going to start up my screen. Oops. I want to go to this screen. Oops, I need to go here. There we go. So if you're interested about some of these technologies, they're available on our website. For example, if you want to learn about spectral accuracy, you can go to the technology menu and look up spectral accuracy. It includes the link to that journal paper. You can, if you go to the technology section, you can look up auto RI, and it explains in more detail how it works. And you can also go to the products page and get more information about the product. And if people are interested and want to try this on your own data, and we do this all the time, it's very popular and it's very impressive, especially since we don't know anything about your data. We're happy to work with you. You can send us a sample data file that you're having problems with, and we can run it through the software and show you how it works. And you can talk to any of us, myself. This is my email address. This is Yongdong's email address, and or you can just hit us up on the general info at cernobioscience.com. So with that, let's open it up for questions.
Thank you, Don, for the excellent walkthrough and demonstration. Again, if you have any questions, there are 3 under Q&A already. You can add to that Q&A list of questions, so we'll go through them one by one. So the first question down is, do I have to acquire GCMS data in the profile mode for Gcid?
Oh, that's one thing I forgot to show. I skipped that part. No, you don't. That's something was requested, and that's new in our version 3, is you don't need to use profile mode data. Now, if you don't use profile mode data, you won't get accurate mass, obviously, because you need to run profile to do that. But you will get the advantages of deconvolution, and you'll get the advantages of the retention index and the forward reverse search algorithms that help you determine the quality of the match and help you determine if you have a mixture. And so that's new in this software. I apologize. I forgot to show you that one, but what it means is, it means that you can have data that you've collected for another project that you probably collected in centroid mode, and you're having a problem identifying something, you can run it through this software, and it's going to help you confirm the proper identification based upon those additional metrics. What it also means that you can take data that you ran 10 years ago in centroid mode and run it through the system and identify the compound that maybe you didn't get right 10 years ago. So it's a nice solution. It doesn't give you the accurate mass, but it gives you everything else, and a lot of times that'll solve the problem.
I got another question down that's coming through the chat box. It says that your explanation was great, was wonderful. The question is whether the same or similar approach can be applied to 2D chromatography.
2D chromatography. Well, you get another level of separation. I have no idea, and I haven't even thought it through, how you would do retention. I guess you could figure out a way to do it. I'd have to really think about that. I've never thought about it that much. We haven't run across all that many customers that are doing 2D chromatography. But I would say that I don't see why not. Yeah.
Mm-hmm. It's a great question. Yeah. Another question is for those who wants to use external standards, do they have to use Alkane standards, or they can use their QC standards? No,
you don't. You can use any compounds that you want. In fact, some people, what they'll do is they have a test mixture or validation mixture that they use, that they run every day on their instrument. As long as you have chromatographic peaks that are spread reasonably well across the run, because if you have a big gap, obviously you can see how these curves work, you're going to have larger errors in retention index. So as long as there's reasonable coverage, you absolutely can use anything you want for a retention index calibration standard. And that's how we do this auto RI. We're actually using identified samples in the run to build the retention index. So no, it doesn't have to be alkanes.
Thank you. The last question here, unless additional questions comes in, is what if the user would not want to change their current workflow? They want to keep it as is.
Well, because we can handle data, we basically read the instrument data file after the acquisition, and we can do all the processing. So one way to look at it is it's kind of you can run our process in parallel to your current workflow, and since we can work with centroid mode data, which is probably what your workflow wants to work with, that's fine. You won't get accurate mass, but you'll still get retention index and the other deconvolution, which in my mind is probably 80% of the power. It's quite powerful. So it would not impact your workflow at all. It can be run in parallel. It can be run on every sample, or it can be run just on samples that are problematic.
Okay, there's another question coming. what if there's a novel compound that's not in the library yet?
Okay. If there's a novel compound that's not, well, if you've identified, well, the question could be taken is if you have a new compound, you've identified it, but it's not in the library, you can build a user library. In fact, our new version of the software lets you add that data into a user library. Just you do 2 clicks and it goes into the library. If it's not in the library and it's still an unknown, I call an unknown because you don't even have it in the library. The only thing you can really do is you can use the formula identification to try to tease out the structure. If you think about MSMS, you're doing fragmentation and experiments to try to back out the structure. If you think about EI, well, yeah, all the fragmentation kind of happens at once. It's highly energetic, but you do get fragments and they do give you clues to the structure, but you do have to work your way back and they're not easy problems. And people spend weeks with very powerful tools to try to do that kind of a thing. And ultimately to confirm it, they wind up synthesizing the compounds. So it's not particularly easy, but you do have a start. And for example, you can if you could be confident of the molecular ion, you might have to run CI to do that. You can go to something like ChemSpider and you can look at the logical structural candidates. And then there are tools that will help you analyze what the fragmentation patterns are for those structures. So it gives you a start. It definitely can help you out.
Thank you, Don. So we're right on the dot. Thank you all the attendees for spending the time with us. Do contact us if you have additional questions or would like to learn more about our product and our offerings, or if you'd like to do a real data demo with any of our softwares. Thank you so much and have a good rest of the day. So with that, we'll close the session.
All right. Thank you very much, everybody.